By the way, I should say that for any of the problems that I'm talking about here, you can of course look that up on my website. The ones that I'm in the middle of right now, in fact, are the very important topics. And as you notice, I've talked about, let's see, actually not about seasons yet, but I've talked about moon's phases so far, and I'll be talking about some of the others here in a moment: gravitation, seasons, Kepler's laws, and so on. And of course, in your book and any other resources that tell you about these topics. Okay, so explain why we have seasons. Well, this particular picture shows it actually pretty nicely. Actually, there's a mistake. I'll point out that mistake in just a moment. In the winter, we have a small arc, a low and small arc, which means less daylight, and it means less intense radiation. In the summer, we have a high and large arc, and that means more intense radiation from the sun and longer days. As we know, especially in Alaska, we have very long days in the summer and very short days in the winter. Here's actually the mistake in this particular drawing. I chose it at some point because it shows it really well what it's supposed to show, except it makes actually a blunder in here. That sun arc up here should continue nicely down this way. So kind of, I was actually out of picture here. Should be nicely down this way here into the northeastern horizon, and same on the other side, kind of nicely in the northwestern horizon. And in the winter here, it should be a small arc through the southeast, and then here into the southwest, while the actual picture here shown kind of looks like the sun is rising in the same spot no matter where, no matter when, winter or summer, and that is not true. This one is a small arc, this one here is a large arc. So I apologize actually for this particular picture, but it shows at least half of what I wanted to show. In any case, those two things, different length of daylight as well as more or less intense radiation, are caused by the tilt of the axis. In the winter, it's in our northern hemisphere winter, our part of the axis, our hemisphere, is tilted away from the sun, and in the summer it's tilted towards the sun. And that happens so because of our own orbit as we go around the sun. Half a year later, our tilt in the northern hemisphere is towards the sun, and again half a year later it is facing away from the sun, pointing away from the sun. So those four things, orbit, tilt of axis, especially tilt of axis, and that those two things produce then the length of day and the more or less intense radiation from the sun. Describe how an observer at a location in the northern hemisphere perceives everything that's relevant to seasons on January 4th. That is, describe the sun's motion and positions in the sky and at what times on that day, and what that means for how heat is reserved. So January 4th in the northern hemisphere, we would be in winter, and this actually doesn't take really a whole lot of astronomy knowledge, but just things that we have already observed on a day-to-day basis, even without having taken astronomy. So we would see that the sun in the morning rises kind of in the southeast around 9 or 10, so late in the morning. Then it's going low in a low arc through the sky at its highest point just above the southern horizon, and that is around noon or maybe 1 o'clock. And then it sets relatively early, around 3 to 4 or so in the southwest. And what that means for how heat is received, well, the sun is very low, and so the radiation is not very intense at all, and of course the daytime is short, so we get little heat overall. If you took a picture of the sun on that January 4th and compared it to a picture that was taken on July 4th with the same camera, how would the size of the sun compare, and why? Well, the sun would appear a little bit larger on January 4th And the reason why is that on January 4th we're a little bit closer to the Sun, and that makes the Sun appear a little bit larger. Notice that neither one of these here was ever mentioned and has anything to do with any of these topics that I talked about. They're totally unrelated, and one doesn't cause the other. Newton's law of gravitation. Newton's law of gravitation says that there is an attracting gravitational force between any two masses. When you drop your pen from 20 inches above the table, it falls towards Earth because of Earth's mass that exerts this gravitational force on the pen. Does the Earth also fall towards the pen? Argue by evoking Newton's law of gravitation. Yes, it does, because that's what Newton's law of gravitation says, that the two masses are attracting each other. Therefore, the Earth also falls towards the pen. That would be the answer to the question. Now, some confusion could arise here. Well, we don't see the Earth falling towards the pen. Well, we don't, and the reason is that the Earth's mass is so large that the force between the two really doesn't matter a whole lot to the Earth, and it falls with such a small acceleration towards the pen that we don't perceive it at all. Question B, if you were on Jupiter's moon Io, the pizza moon, would the pen fall down towards Io's surface as well? Explain. Again, Newton's law of gravitation says that any two masses attract each other. We're on Jupiter's moon Io and dropping a pen, and yes, it does fall towards the moon Io because the two attract each other gravitationally. Now, some people could argue that, well, but Jupiter exerts such a large gravitational force as well, and yet that's true. What Jupiter does to Io, it kind of stretches, it gives it large tidal forces that stretches Io and gives rise to its volcanism, and so yeah, we could say as well, but it's not, the pen isn't floating here or something, because if it was, then everything on Io's surface would be floating, and that's not the case. So Jupiter does take a little bit away from it falling down, but it still falls. And either way, with this question is about the gravitational force. Either way, the pen is attracted by Jupiter, the pen is attracted by Io, Io is attracted by the pen, Jupiter is attracted by Io, and so on. And that's what this question really is about. Okay, retrograde motion. Why do planets seem to move backwards? And I have a couple of examples here. This is the motion of Jupiter in Taurus. This is from some pictures that I took in 2000 and 2001, and they happen, both of them, Saturn is over here, Saturn and Jupiter happen to be in the same constellation of Taurus, and that's how I got the plot. And so why do planets seem to move backwards? Well, they orbit the Sun nicely on an ellipse, but of course we orbit the Sun as well on an ellipse, and as we're getting closer to an outer planet, it seems that that planet is turning around. So here Jupiter orbits nicely on its ellipse. It keeps orbiting on its ellipse, but because we're faster and closing in on Jupiter, it seems as if Jupiter is moving backwards, retrogrades, for quite a while. This is almost up to half a year or 4 months or so. And then once we have passed it far enough, then it seems to regain its original motion. Notice at all times it has been moving right to left, west to east, across the sky, across the stars. But this is only an illusion for us, albeit it's an illusion that we can capture on film. Tidal forces. Name as many examples of tidal forces as you can. Again, this is something you will find in my very important topics, as well as in peculiar planets. I mentioned those in here several times. Among these are, of course, ocean tides on Earth, rock tides on Earth, as well as the synchronous rotation of most moons. Among them are Saturn's rings. Among them are Shoemaker-Levy 9, the comet that plunged into Jupiter was ripped apart by its tidal forces. And there are a few more examples.